So the hydrogen. So for the hydrogen atom, what do we have in it? Huh? You have a proton in the middle and an electron going around it, right? So the potential, for hydrogen, the potential is, remember the potential is K, Q1, Q2 divided by R. K is 1 over 4 pi epsilon naught. Q1 is, one of them is plus, the other one is minus E. So we get minus E squared over 4 pi epsilon naught times 1 over R. So notice R is the distance from the center. So there is spherical symmetry. So we're going to use what you would use would be spherical coordinates. So this, the Laplacian here, it doesn't make sense to go with Cartesian coordinates because it will make your life even harder. So you'll use spherical coordinates. So the Laplacian here that you will have to multiply by is what you just coded. Del squared is no longer just this. It's going to be 1 over r squared, 1 over r squared, dr of r squared r plus 1 over r squared sine squared of phi. Because here we're using spherical coordinates, no longer x, y, z, r, theta, and phi. Those are the coordinates I use. Second derivative with respect to theta plus 1 over r squared sine phi times sine all this to replace just this guy. Okay. And then you plug in your equation, you plug in for u, you plug in this, and then you try to solve this equation. Right? You try to solve that equation. Now you will run into problems if you try to solve it directly, so what you do is you try to separate the variables. You would assume the equation psi, which will be a function of r, and theta, and phi. You would assume it's a product of three functions, just like we did earlier, separated the variables. You would assume it's a product of three functions. A function, capital R, that depends only on little r. A function, capital theta, that only depends on theta. And a function, capital phi, that only depends on little phi. Plug it in, and then do some math, take derivatives, and then you will find that the equation is separable. And then you will get solutions. Okay? You will get solutions. The very first thing about the solutions that you will get the correct energy levels that the Bohr model gave you, or the experiments also gave. Because remember, when you get a new theory, the new theory needs to explain the old theory, right? It needs to continue to explain the old stuff that the previous theory did, plus some more, plus the new stuff that the old theory did. So yeah, so it will give you the right energy levels. It will tell you that this, En. So now we haven't solved it, right? We just stated it. We haven't solved it. So now I'm stating some facts. So it will tell you that En is equal to minus 13.6 EVs divided by N squared. N is called the principal quantum number. Is the principal quantum number. And again, it will come out from the math. These functions here, R and theta and phi, they will depend on three quantum numbers. One of them is N, other one is L, and the other one, the third one would be M. And they're related to each other. The next one would be, so capital N was the principal quantum number, and then the orbital quantum number will have a letter L here, would be called the orbital quantum number. And it's given by this. L is equal to 0, 1, all the way to n minus 1. It's always one less than n. It starts at 0 and then goes all the way to n minus 1. And then there is the magnetic quantum number. And I will tell you what it is, and then we will state their relevance. The magnetic, let me call it ML. It's the magnetic quantum number. And this ML it runs from 0 to plus or minus 1, plus or minus 2, plus or minus L. So let's do a couple of examples to get the relevance of these, or to get them down. Let's do an example here. Let's say, suppose n is equal to 1. What is L? Or what could L be?
0.
Yeah, because L starts at 0 and it could be up to n minus 1. So since n is 1, so it can only be 0. So yeah, so this means L is equal to 0. How about ML? From 0 all the way to L plus or minus L. So since L is 0, so ML is 0, right? Let's do something a little more interesting than that. Suppose n is equal to 2. Then what could L be? Could be 1, could also be 0. Okay. It goes from 0 all the way to n minus 1. So L could be, let me write 0 first, and then it could be 0 or 1. How about ML? Let's list them.
-1.
It could be -1, +1, and 0, yes. So ML basically goes like this. So ML is from minus L all the way to positive L in steps of 1.
Can they be ML -1 and L 0?
No.
No.
So for each value of L, ML could be
It matches
or
it with
minus,
positive
yes.
or negative.
Yeah. Now, what's the significance of L? L tells you what's the total angular momentum. So the total angular momentum, the magnitude, capital L is the magnitude of the angular momentum. How much is it? Well, again, I'm just stating, it comes out from the equation also. It is L times L plus 1 square root times HY. Now the Z component of the angular momentum, we usually choose one value, we choose one axis to find the Z component. We could have chosen the X axis or the Y axis, but usually people choose the z-axis because what happens is when you apply a magnetic field, the energy levels split. I will tell you in a little bit what the energy levels, how they split, why. But we usually choose the z-axis to figure out the z component. So Lz turns out to be equal to ml times h bar. That's Lz, the z component of the orbital angular momentum.
Would it be different in the other ones? If it was Ly?
No, if you choose the y-axis to be the chosen axis, then you would just have ml times h bar. Now, here's the thing. Lz, you will notice, will always be less than capital L. Because this one, at best, is going to be L times h bar. But this one is L times L plus 1, and then square root, which is always greater or equal than L. Right? It's always greater than. And you might think, why can't Lz be just equal to L? Right? Because if I take a wheel and I spin it, right? If you take a wheel and you spin it, in what direction is the z moment? Is the angular momentum if the wheel is spinning this way? Yeah, the angular use your right hand rule. So the angular momentum would be in this way for a macroscopic, right? For a big wheel. So the wheel is spinning in the x-axis, in the xy plane. The momentum is in this direction. So I will just choose my z direction to be along the total momentum, and the total momentum is equal to the momentum in the z direction. So they're equal to each other. But you can't do that in quantum. Why? So imagine your electron is spinning this way. Imagine you get a circle, the electron is spinning this way. So it's spinning along the xy plane, right? So its z component, it's the position in the z direction is now. It's, let's say this is the 0, right? This is z equal to 0. So you know the z position exactly right. You know the position in the z direction exactly. Quantum, the uncertainty principle says you can't know the momentum exactly in the z direction. So you can determine both at the same time. Let's do, I wanted to do an example. Let's say L is equal to 2. Suppose L is equal to 2. Here's the question. Find part A, find capital L, and B, find the maximum Lz can be. What's the maximum that Lz can be? Who can give me an idea on how to do this? Plug it in, right? Yeah. So L equal to, this is 2, so 2 times, so it's going to be 2 times 2 plus 1, h bar, which is square root of 6 times h bar, right? And how about Lz, the maximum it can be? How big can Lz be? It's ml times h bar. How large can ml be? Yeah, it can be as large as L, right? It could be 2. So it would be twice h bar. I'm just curious if that's okay. So here's what we're saying. Here's the z. Here's L. It's the square root of 2. No, square root of 6 h bar. And here's its z component. Lz is equal to twice h bar, and they make an angle theta with each other. Remember, in spherical coordinates, you measure theta from the z-axis, right? And phi is along the on the y, on the xy plane. So, can we determine that angle theta? Of course. just cosine inverse of this over this, right? So we can determine theta. So theta is the cosine inverse of LZ of this one. So that would be 2 over square root of 3, 2 over square root of 6, because each part cancels. And that gives 35.3. Decrease. So you can't just have any angular momentum you like, it's quantized. Spectroscopic notation from chemistry for different energy levels, you will have different shells and different orbitals, right? Remember S, P, D, F, G, H, yeah. So states with angular momentum equal to 0, they're the S states. So let's just do a couple of examples here. N, L, and then the notation. If n is 1, n cannot be 0, right? N is 1. Then how much what is L? 0. And this is, the notation is 1s. If n is 2, what can L be?
0.
Could be 0, and it could be 1. So if n is 2, you have 2 possibilities for L. So you can have 2s, and when L is 1, that state is called P. SP. That's just one more. 3. For 3, you have 3 possibilities. L equal to 0, or 1, or 2, right? So for this one, you have what? 3s, and this one? 3 P, and this one? 3, who remembers?
Q.
D.
Close.
Close. I actually forget what they stood for. There is something they stand for. SP. Huh? Yeah, so they stand for something. Okay. Let's see. Here is a question. How many different states? How many distinct N, L, ML states of the hydrogen atom with n equal to 3 are there? So if n equal to 3, how many distinct states are there? What I mean by states, I mean labeled by N, L, and M, L. There is a fourth quantum number, which is the spin. I haven't mentioned yet, but I will mention it later. Hopefully. So the different states are this. So you can have n equal to, well, n is 3. And for this state, you can have L equal to 0, in which case you have ML is also equal to 0, right? You can have L equal to 1, in which case ML could be what? Yeah, -1, 0, and 1. Or you can have L equal to 2, and in that case ML is -2, minus 1, 0, 1, 2. So if you count right, I have one state here, I have 3 states here, and I have 5 of them here, right? So in total, you have 1 plus 3 plus 5, right? Which is 9. Which is 9. If you add spin up, spin down, it will be actually 18. It would be 18. If you remember from chemistry, as you fill up the orbitals, the first one holds 2 electrons, right? 8, 18, and yeah. The next one will be 32. Remember this from adding series in calculus? We got 3, when you add the odd numbers, you got the number of terms, so 3 terms, so squared. Just 3 squared is 9. Anyways, low trick. Let's see. I think this stuff is not very relevant. I will go to the next one, which is the probability density. So when we have spherical symmetry here, technically, to figure out where the particle is, I need to integrate from 0 all over the volume. All over the volume means you integrate from, for r, from 0 to infinity, theta from 0 to pi, and then phi from 0 to 2 pi, right? That way it would span all space, right? But because we have spherical symmetry, the integrals from theta and phi will give us 4 pi. Will give us a 4 pi. And then the integral becomes this. To normalize a function, we need or the probability would be 1 if I integrate all over space from so all space, of psi squared the volume. And if you remember, dv in spherical coordinates is r squared sine theta dr theta. So these guys, sine theta, d theta, dp will give you a 4 pi, and so you get here, your integral will become from 0 to infinity of sine squared r squared dr is 4 pi. This needs to be you integrate all over the space. Now I haven't given you psi yet. I haven't given you that wave function psi. In the next worksheet, I will give you different wave functions for different energy levels, different L also, L and L. But I will just give you one. Remember A, the Bohr radius. Was 0.529 times 10 to the minus 10 meters, right? The wave function when n equal to 1, which means L equal to 0, ML equal to 0, that wave function is this. The ground state wave function. The ground state wave function, state wave function. And in this context, when I say the ground state, I mean for what system? Infinite square well or hydrogen? Hydrogen, yeah. So we're talking about hydrogen, so hydrogen. Yeah. So the wave that wave function we can call it the 1s state because n is 1, of course L is 0, so s. It is 1 over pi a cubed e to the minus r over a. That's the function. can verify this, we can check. It's normalized, that it is normalized, meaning this. If I do 4 pi times the integral from 0 to infinity of psi squared, what is psi squared? If you square this, you will get 1 over pi a cubed, right? Pi a cubed. E to the, when you square here, you get a 2 minus 2r over a, and then r squared dr. If you integrate this, you will get 1. How would we integrate this function? To get 1.
The separable parts.
Integration by parts?
Yeah.
Yes. Cool. So, and you will integrate by parts actually twice. Integrate by parts, you get rid of, you will let u equal to r squared the first time, and then it becomes an r, and then let u equal to r the second time, and then you will be able to integrate. Or maybe there is another trick. There might be. Oh yeah, another way is to do parameter differentiation, like we did last semester. Just yeah, you can do parameter differentiation. Anyone remembers parameter differentiation? If you treat, huh? Yeah. You can call 2 over a, name it alpha. So if you take the derivative with respect to that alpha, an r comes down each time. So
Also like a shoestring or a horseshoe or something like that. Shoestring method?
A table format, right?
Yeah. You
I-
can make a table.
oh, okay, okay. I'm not familiar with that method, at least.
You like take the integral
It's
of
down
everything
here.
until it goes to,
Plus r is going to 0, so.
you take the derivative of something until it goes to 0 and then
Okay.
integrate everything.
Okay. I think that's parameter differentiation, probably. Yeah. So, anyways, however way you do it, or ask ChatGPT.
Absolutely, yeah.
Or Wolfram Alpha, or something.
On the exam?
No, in by hand. So I would not. I would not do it right now. But here is the. So yeah, it will give you 1 because this integral here turns out to be the following. I'm going to just write it down. You will have. When you cancel, you get 4 over a cubed times minus a r squared over 2 minus a r minus a squared r over 2 minus a cubed over 4. And so evaluate between 0 and infinity. No, I forgot my exponential. That's the one that matters the most, right? Minus 2r over a. 2r over a. And this integral from 0 to infinity. Notice that infinity, the exponential will destroy everybody, just 0. Nothing grows or goes to 0 faster than it, or goes to infinity faster than this one. Goes to 0. And then at 0, at the lower limit, this is 0, and this is 0, the exponential is 1, and this one is just a cubed over 4. It doesn't depend on r. And so you just get 1. Okay. So that's, so it is normalized, it's a normalized function. And then they ask, what's the probability that you will find the electron within the Bohr radius? Meaning the electron between 0 and a. So what's the probability? Within the Bohr radius. what would you change here?
Instead of infinity, you say like add to 9.
Exactly, to A. Just plug in A, right? So from 0 to A. So instead of infinity, you will put A here. And when you put A, you'll have A cubed, and then R is A, so you get A cubed and A cubed. That cancels this A cubed on the outside. And so, so you will, yeah, so just do that. And you will need to use a calculator probably. So it turns out that the probability is, I would just write it down, it's gonna be 1 minus 5e to the minus 2, and that is 0.32. That would be the probability. Yeah. Okay. One last topic here for today. We'll just start it.